Okay, I'm Bryan. So I'm a VP of Engineering at Veridise. So in this talk, I'm going to introduce Medjai, our formal verification tool for Cairo smart contracts. And here's the motivation. So as we're all aware, bugs in blockchain software have very serious implications, especially loss of financial assets. So note that these bugs are not just limited to one ecosystem. You can see that they're affecting, Ethereum, Binance, and more. Consequently, this leads to a lot of loss of trust in these affected ecosystems. We also wouldn't want Starknet to also be affected as well. But unfortunately, smart contracts written in Cairo, the programming language that Starknet contracts are written in, they're not immune to bugs. So to avoid the type of hacks that we've just seen on the previous slide, we absolutely want to make sure that we minimize the number of bugs in our smart contracts. So to do this, we need to be proactive about finding the bugs, fixing them, and making sure that new ones don't surface in our smart contracts. So let me tell you a little bit more about our company first. Veridise is a blockchain security company that provides security audits and state-of-the-art security tools for all layers of the blockchain ecosystem, including Starknet and Cairo smart contracts. We hunt down bugs in our client's code and/or prove that the code is consistent with the intended behavior. Okay. One of our services includes a web service that we call the Software as a Security platform. Security as a Service platform. In a nutshell, Veridise builds automated security analysis tools that can give you real-time feedback about bugs and security vulnerabilities. We make these tools available through our Security as a Service. The way this works is that as a smart contract developer, you'll upload your Cairo smart contract source code as well as a programmatic description of the intended behavior of your smart contract to our servers. After our service receives your job submission, our tools will analyze your code with respect to the intended behaviors and produce a list of issues uncovered by our tools. So the reason why you would want to use our platform is because it's tuned by our engineers, so smart contract developers don't have to worry about having to install these tools or trying to get the right hardware for them. In addition, because our formal specification language is designed to be both blockchain and language independent, our platform allows specs to be reused across all of our tools and for different languages and blockchains. Our tools make extensive use of the latest research, the latest academic research, into formal methods. For those of you unfamiliar with the term formal methods include mathematically rigorous techniques for finding bugs and/or security vulnerabilities, as well as being able to construct mathematical proofs about the correctness of software or hardware. At Veridise, we are using 3 different types of formal methods: automated testing, stack analysis, and formal verification. They each have their pros and cons, but tonight I want to focus on formal verification. Formal verification is useful if you want to mathematically prove that there are no bugs in the code. In unit or integration testing, a developer sets up a specific scenario and checks if the code behaves correctly in that specific scenario. However, this only works for one scenario. In contrast, formal verification can reason about all possible ways a piece of code can be executed. This includes tricky edge cases that the user has not thought of. Thus, formal verification can make the strongest guarantees that the code does what it is intended to do, but typically with a trade-off that the developer must tell the tool what the code is intended to do. Therefore, formal verification is typically semi-automated in that it requires additional input. So the subject of my talk will be Medjai, an open source automated formal verification tool that we've developed at Veridise. You can think of Medjai as a tool that takes as input 1, the source code of your Cairo smart contract, and 2, a programmatic description of the contract's intended behavior, which we call a formal specification. Medjai will either prove that the code performs the intended behavior, Or it will alternatively find a set of examples that show that the intended behavior does not actually happen. In other words, a bug. As an example, let's consider the move function from a Cairo port of the MakerDAO's VAT protocol. This function is used to transfer RAD amount of DAI stablecoin from source to destination. This is done by subtracting RAD from the destination account's balance and then adding RAD to the source account's balance. So one interesting thing to note here is that RAD is expressed as a UN256, which is larger than a single Cairo field element. Thus, we have to express a UN256 as a pair of field elements, one for the high bits and one for the low bits. Keeping this in mind, it will soon become clear that there's actually a bug in the snippet that is shown here. Using Medjai, we can automatically discover this bug by thinking about the intended behavior of this function. In particular, we expect a move to transfer funds from source to destination. This means that move should satisfy the following property. The destination account's balance either stays the same, account balance either stays the same or decreases. If we feed this function as is into Medjai, then Medjai will treat this specification as a sort of compile time assertion and check it without having to actually execute the contract. For this snippet, Medjai will produce a counterexample, an actual value of RAD showing that the destination's DAI balance can actually decrease, which is the opposite of what we intend, and that the source's DAI balance can actually increase, which again is also the opposite of what we intend. The problem is that both of the field elements that make up the UN256 may actually be out of bounds of UN256, so this can result in integer overflow. This overflow, again, allows the destination's account balance to actually decrease or the source's account balance to actually increase, which means that people could, for example, arbitrarily create funds or destroy other people's funds. So let's suppose instead that the developer will fix this bug by inserting a function call to check that the RAD is indeed a valid UN256. If we feed the fixed code back into Medjai, then Medjai will show that the fixed code actually implements the behavior that we have described here. That is, Medjai can prove mathematically that is always the case that the destination's DAI balance increases and that the source's DAI balance decreases. This was an actual bug that our Medjai team found in the MakerDAO Cairo code. And Medjai helped ensure that MakerDAO's fix actually worked here. The takeaway here is that the only thing we had to do to detect this bug was to feed in a fairly obvious specification of what this move function should do. And then Medjai was able to automatically discover the subtle integer overflow bug, which would have been hard to detect normally. And I also want to note that this move function is also just a few lines of code. It's fairly straightforward, but even though it is fairly straightforward, it was still easy to introduce bugs here. Okay, so the specification that we provided to Medjai was actually crucial in being able to detect this bug. So I want to talk about the spec in more detail. We can write down the specification that I just showed previously in plain English as vat.move causes the destination's DAI balance to only increase and the source's DAI balance to only decrease, and that all other DAI balances should stay the same. In essence, what this informal specification captures is some effects of calling the move function. A smart contract developer can then spend 1 or 2 minutes to translate that written description into the formal specification that I've shown here. This specification is written in a language that we call V, which is a specification language we've designed at Veridise to make it easy for smart contract developers to write formal specifications. We can pass these specs into our tools, such as Medjai, which will then use these specs to construct mathematical proofs. So let's break down the meaning of the specification. In a V specification, the smart contract developer must describe intended behavior by providing 3 pieces of information: what transaction happens, when this transaction happens, and what this transaction is intended to do. Let's start by specifying what transaction happens. We can think of blockchain transaction history as a linear sequence of transactions. Within this imaginary history, the smart contract developer can indicate the transaction by writing the actual function call that is going to be performed. For example, if the developer wants to indicate rad amount of DAI is moved from source to dest, they can simply write a call to the move function. When this transaction is done executing, it either finishes successfully or it reverts. So we indicate when the transaction is done and that it is successful by writing this finished action. The last part we need to understand is what this transaction is intended to do. Developer can write out this intention by writing basically the logical expressions that would be very similar to assertions in normal program code. The first 2 dark blue lines correspond to what we've seen before, the relationship between the new and the old DAI balances. There is, however, one new clause in this big AND expression, which is that all of the DAI balances, except for the source and destination, are going to remain the same before and after the transaction. While this is a construct that is very specific to our V specification language, we hope that convenient expressions like these make it easier to read and write common properties. In summary, what we've seen here is that the V specification is able to capture the properties we care about in a convenient way. Furthermore, note that there is nothing about the specification that is specific to Cairo. V is designed to be tool, language, and blockchain independent, so we could have even originally written this spec for the Solidity version of MakerDAO, and then used the same spec for the Cairo implementation. So now that we understand what type of inputs we need to provide to Medjai, I'll now show a video demo created by my colleague who wasn't able to make it to this event of how we can run Medjai on the MakerDAO example using our security as a service platform.
In this demo, we'll see how Medjai can be used to find bugs in real-world Cairo programs, as well as prove the absence of bugs with respect to a specification. Specifically, we'll take MakerDAO's VAT protocol as an example. The function move within the VAT protocol takes as input a source user, a destination user, and an amount of funds to be moved from source to destination, named rad. To describe the correctness of move, we've constructed a specification in the V language. This specification states the following. Consider an arbitrary user named other. Given that the balance of DAI in the source and destination are valid uint256 values, and that the other user is distinct from both source and destination, then after a call to move, 1, the source's DAI balance decreases or stays the same. 2, the destination's DAI balance increases or stays the same. And 3, the other user's DAI balance stays the same. To check that this specification correctly describes the move function, we can give both the source code as well as the specification to Medjai through our web interface. You can upload the source code here, as well as upload specifications here. I've already uploaded this code and specification, so I can start the job here. As the job runs, Medjai will give information about its progress. Through the interface, we can see that Medjai found a bug. With the reported bug, Medjai will give an assignment of variables that developers can use to replicate the bug. By doing so, a developer for the VAT protocol could find that their move implementation is missing a check on the input value rad for validity. After fixing the bug, we can pass our new source code into our web interface for Medjai, keeping our specification the same. Again, since I previously uploaded this fixed code, we can go ahead and run Medjai. Now that our program is correct, Medjai reports that no bugs are found. This means that the move function behaves exactly as our specification describes.
Okay, so let me go back to the slides. All right. So I hope that you've enjoyed what you've seen about Medjai today. By the way, Medjai is open source, so again, you can check out the source code on GitHub if you'd like to. If you're interested in Medjai, the SaaS, or other Veridise services, feel free to reach out to us over Twitter or email. Or you can contact me directly while I'm here, or you can message me on Telegram. I'll be happy to answer any questions now. Yeah, so the question is how verbose is V? So basically, we've designed V to be as programmer-friendly as possible. So you would basically write your assertions in V, but without having to do any tedious stuff like trying to initialize your contracts or try to set up transactions in a specific way. With V, we can express not just properties over states in time, but we can also express things like preconditions and postconditions. So for example, if you want to make any assumptions about when a call happens, you can add that as a precondition. And if you want a stronger property, you can add that, you can add additional postconditions.